Good morning, good afternoon, and good evening, everyone. And welcome to this big data tutorial from Simplilearn, where we will learn on big data and its various aspects. We will start with understanding evolution of big data and why and what is big data. Why are organizations interested in big data and what are they looking in this so-called big data for their benefits? Then we'll look at the challenges of big data and what is the need of a solution to work, handle, store, capture, process, or analyze this big data. We learn about Hadoop as a solution, which is a framework. We learn its storage layer architecture, that is HDFS, which stands for Hadoop Distributed File System. We learn on MapReduce algorithm and processing framework, and then we will have a demo on HDFS and MapReduce. So this is the list of topics which we'll be covering in today's session. Now, when we talk about evolution of big data, we have known that data has evolved in last 5 years like never before. Now, in fact, before going to big data or before understanding these solutions and the need and why there is a rush towards big data technology and solution, I would like to ask a question. Take a couple of minutes and think, why are organizations interested in big data? Why is there sudden rush in industry where everyone would want to ramp up their current infrastructure or would want to be working on technologies which allow them to use this big data? Think about it. What is happening and why are organizations interested in this? And if you think on this, you will start thinking about what organizations have been doing in past, what organizations have not done, and why are organizations interested in big data. Now, before we learn on big data, we can always look into internet and check for use cases where organizations have failed to use legacy systems or relational databases to work on their data requirements. Now, over past 5 years or in recent decade, what has happened is organizations have started understanding the value of data, and they have decided not to ignore any data as being uneconomical. Now, we can talk about different platforms through which data is generated. Take an example of social media like Twitter, Facebook, Instagram, WhatsApp, YouTube. You have e-commerce and various portals, say eBay, Amazon, Flipkart, Alibaba.com. And then you have various tech giants such as Google, Oracle, SAP, Amazon, Microsoft, and so on. So lots of data is getting generated every day in every business sector. The point here is that organizations have slowly started realizing that they would be interested in working on all the data. Now, the question which I asked was, why are organizations interested in big data? And some of you might have already answered or thought about that organizations are interested in doing precise analysis, or they want to work on different formats of data, such as structured, unstructured, semi-structured data. Organizations are interested in gaining insights or finding the hidden treasure in the so-called big data. And this is the main reason where organizations are interested in big data. Now, there are various use cases. We can compare that organizations from past 50 or more than 50 years have been handling huge amount of data. They have been working on huge volume of data. But the question here is, have they worked on all the data or have they worked on some portion of it? What have they used to store this data? And if they have used something to store this data, what is happening? What is changing now? When we talk about the businesses, we cannot avoid talking about the dynamism involved. Now, any organization would want to have a solution which allows them to store data and store huge amount of data, capture it, process it, analyze it, and also look into the data to give more value to the data. Organizations have then been looking for solutions. Now, let's look at some facts that can convince you or that would convince you that data is exploding and needs your attention, right? 55 billion messages and 4.5 billion photos are sent each day on WhatsApp. 300 hours of video are uploaded every minute on YouTube. Did you guys know that YouTube is the second largest search engine after Google? Every minute users send 31.25 million messages and watch 2.77 million videos on Facebook. Walmart handles more than 1 million customer transactions every hour. Google, 40,000 search queries are performed on Google per second. That is 3.46 million searches a day. In fact, you could also say that a lot of times people, when they are loading up the Google page, is basically just to check their internet connection. However, that is also generating data. IDC reports that by 2025, real-time data will be more than a quarter of all the data. And by 2025, the volume of digital data will increase to 163 zettabytes. That is, we are not even talking about gigabytes or terabytes anymore. We are talking about petabytes, exabytes, and zettabytes. And zettabytes means 10 to the power 21 bytes. So this is how data has evolved. Now you can talk about different companies which would want to use their data to take business decisions. They would want to collect the data, store it, and analyze it. And that's how they would be interested in drawing insights for the business. Now, this is just a simple example about Facebook and what it does to work on the data. Now, before we go to Facebook, you could always check in Google by just typing in companies using big data. And if we say companies using big data, we should be able to find a list of different companies which are using big data for different use cases. There are various sources from where you can find. We could also search for solution, that is Hadoop, which we'll discuss later, but you could always say companies using Hadoop, and that should take you to the wiki page, which will basically help you know what are the different companies which are using this so-called solution called Hadoop. Okay, now coming back to what we were discussing about, so organizations are interested in big data, as we discussed, in gaining insights. They would want to use the data to find hidden information which probably they ignored earlier. Now take an example of RDBMS. What is biggest drawback in using an RDBMS? Now you might think that RDBMS is known for stability and consistency, and organizations would be interested in storing their data in Oracle or DB2 or MySQL or Microsoft SQL Server, and they have been doing that for many years now. So what has changed now? Now, when we talk about RDBMS, the first question which I would ask is, do we have access to 100% of data being online in RDBMS? The answer is no. We would only have 10 or 20 or 30% of data online, and rest of the data would be archived, which means that if an organization is interested in working on all the data, they would have to move the data from the archived storage to the processing layer, and that would involve bandwidth consumption. Now, this is one of the biggest drawbacks of RDBMS. You do not have access to 100% of data online. In many of the cases, organizations started realizing that the data which they were ignoring as being uneconomical had hidden value which they had never exploited. I had read a presentation somewhere which said, torture the data and it will confess to anything. Now that's the value of data which organizations have realized in recent past. Take an example of Facebook. Now this shows what Facebook does with its big data. And we'll come to what is big data, but let's understand a use case. Now, Facebook collects huge volumes of user data, whether that is SMS, whether that is likes, whether that is advertisements, whether that is features which people are liking, or photographs, or even user profiles. Now, by collecting this data and providing a portal which people can use to connect, Facebook is also accumulating huge volume of data. And that's way beyond petabytes. They would also be interested in analyzing this data. And one of the reasons would be they would want to personalize the experience. Take an example of personalized news feed. Depending on a user behavior, depending on what a user likes, what a user would want to know about, they can recommend a personalized news feed to every particular user. That's just one example of what Facebook does with its data. Take an example of photo tag suggestions. Now, when you log into Facebook account, you could also get suggestions on different friends whom you would like to connect to, or you would want to tag so that they could be known by others. Some more examples which show how Facebook uses its data are as follows. So the flashback, collection of photos and posts that receive the most comments and likes. Okay, there was something called as I voted that was used for 2016 elections with reminders and directions to tell users their time and place of polling. Also, something called as safety checks. In incidents such as earthquake, hurricane, or mass shooting, Facebook gives you safety checks. Now, these are some examples where Facebook is using big data. And that brings us to the question, what is big data? This was just an example where we discussed about one company which is making use of that data which has been accumulated. And it's not only for companies which are social media oriented like Facebook, where data is important. Take an example of IBM, take an example of JP Morgan Chase, take an example of GE, or any other organization which is collecting huge amount of data. They would all want to gather insights, they would want to analyze the data, they would want to be more precise in building their services or solutions which can take care of their customers. So what is big data? Big data is basically a term. It is used to describe the data that is too large and complex to store in traditional databases. And as I gave an example, it's not just about storing the data. It is also about what you can do with the data. It also means that if there is a lot of dynamism involved, can you change the underlying storage and handle any kind of data that comes in? Now, before we get into that, let's just understand what is big data. So big data is basically a term which has been given to categorize the data if it has different characteristics. Organizations would want to have the big data stored, processed, and then analyzed to get whatever useful information they can get from this data. Now, there are 5 V's of big data: volume, velocity, variety, value, veracity. Although these are 5 V's, but then there are other V's which also categorize the data as big data, such as volatility, validity, viscosity, virality of data. Okay, so these are 5 V's of big data, and if the data has one or all of these characteristics, then it can be considered as big data, including the other V's which I just mentioned. So volume basically means incredible amount of data, huge volumes of data generated every second. Now that could be used for batch processing, that could be used for real-time stream processing. Okay, you might have data being generated from different kind of devices like your cell phones, your social media websites, online transactions, wearable devices, servers, and these days with IoT we are also talking about data getting generated via Internet of Things. That is, you could have different devices which could be communicating to each other. You could be getting data from radars or lidars or even camera sensors. So there is a huge volume of data which is getting generated. And if we are talking about data which has huge volume, which is getting generated constantly or has been accumulated over a period of time, we would say that is big data. Velocity. Now this is one more important aspect of big data. Speed with which the data is getting generated. Think about stock markets, think about social media websites, think about online surveys or marketing campaigns or airline industry. So if the data is getting generated with a lot of speed, where it becomes difficult to capture, collect, process, cure, mine, or analyze the data, then we are certainly talking about big data. The next aspect of big data is variety. Now, this is where we talk about structured data, semi-structured data, or unstructured data. And here I would like to ask a question. What is the difference? When do you call the data as structured, semi-structured, or unstructured? Now let's look at an example before we theoretically discuss about this. I always would like to use some examples. Let's look at a log file and let's see what is it. So if I look at this log file and if I would say what kind of data is this, which is the highlighted one, the answer would be it is structured data. It has specific delimiters such as space. It has data which is separated by space. And if I had 100 or 1,000 or 1,000,000 rows which had similar kind of data, I could certainly store that in a table. I could have a predefined schema to store this data. So I would call the one which is highlighted as structured. But if I look at this portion where I would look at a combination of this kind of data where some data has a pattern and some data doesn't. Now this is an example of semi-structured data. So if I would have a predefined structure to store this data, probably the pattern of data would break the structure. And if I look at all the data, then I would certainly call it unstructured data because there is no clear schema which can define this data. Now this is what I mean by variety of data. That is structured data which basically has a schema or has a format which could be easily understood. You have semi-structured, which could be like in XML or JSON or even your Excel sheets, where you could have some data which is structured and the other is unstructured. And when we talk about unstructured, we are talking about absence of schema. It does not have a format, it does not have a schema, and it is hard to analyze, which brings its own challenges. The next aspect is value. Now value refers to the ability to turn your data useful for business. You would have a lot of data which is being collected, as we mentioned in previous slides, right? There would be a lot of data wrangling or data pre-processing or cleaning up of data happening. And then finally, you would want to draw value from that data. But from all the data collected, what percentage of data gives us value? And if all my data can give me value, then why wouldn't I use it? This is an aspect of big data, right? Veracity. Now this means the quality of data. Billions of dollars are lost every year by organizations because the data which was collected was not of good quality, or probably they collected a lot of data and then it was erroneous. Take an example of autonomous driving projects which are happening in Europe or US, where there are car fleets which are on the road collecting data via radar sensors and camera sensors. And when this data has to be processed to train algorithms, it is realized that sometimes the data which was collected was missing in some values, might be was not appropriate, or had a lot of errors. And all this process of collecting the data becomes a repetitive task because the quality of data was not good. This is just one example. We can take example from healthcare industry or stock markets or financial institutions and so on. So extracting loads of data is not useful if the data is messy or poor in quality. And that basically means that veracity is a very important V of big data. Now, apart from veracity, volume, variety, velocity, and value, we have the other V's such as viscosity, how dense the data is. Validity, is the data still valid? Volatility, is my data volatile? Or virality, is the data viral? Now all of these different V's categorize the data as big data. Now when we talk about applications of big data, as I said, you could just be looking for companies which are using big data. So we have healthcare industry, something like ICU monitoring, epidemic early warning. You could also have big data solutions which are implemented by pharmaceutical companies to find out if the right amount of medicines and the right required medicines are available in particular regions. And based on this insight, they could then inform different other companies for shortage or about shortage of medicines available in a particular area, or could serve the customers better. Look at transportation industry, airlines, trains, buses, cars. They are benefiting from this big data because now there are solutions available in market which allow all of these industries to use this big data. Take an example of a recommendation system which can inform customers if they could benefit by taking a taxi rather than booking a flight to travel from one location to other location based on each and every customer's preference. Logistic optimization, traffic congestion, these are some examples which we easily see when we use apps like Google Maps or Apple Maps, or if we use maps from TomTom. If we look at other solutions which help organizations or customers benefiting from an app which is processing huge amount of data in the backend. Telecommunications industry. Now this is also an industry which is using big data. such as geomapping, network monitoring, text-to-speech recognition, sentiment analysis, and many more use cases. Retail industry. Now that's benefiting huge from being able to process big data, coming up with real-time algorithms which could offer a better price to a customer while he is in the store or on a particular portal, coming up with the timely analysis of inventory, coming up with right data analysis to prepare on promotional campaigns. Take an example of IT industry. Now this has benefited huge from being able to process big data or being able to store, capture and process this big data. System log analysis, cyber security are some use cases. Financial services, so fraud detection, audit trails, again understanding the customer behavior and deciding on the credit limits, or having a data lineage of the data which flows through the banking systems. So these are some of the applications of big data. We can find lots and lots of use cases. Okay, now here we would like to talk on a big data case study, and we have taken an example of Google, which obviously is one of the companies which is churning and working on huge amount of data. Now it's actually said that if you compare one grain of sand with one byte of data, then Google is processing or Google is handling whole world's sand every week. That is the kind of data which Google is processing. Now in early 2000 and since then, when the number of internet users started growing, Google also faced a lot of problems in storing, increasing user data, and using the traditional servers to manage that. Now that was a challenge which Google started facing. Could they use traditional data server to store the data? Well, yes, they could, right? Storage devices have been getting cheaper day by day. But then, how much time does it take to retrieve that data? What is the seek time? What is the time taken to read and process that data? Thousands of search queries were raised per second, no doubt. Now we could say millions and billions of queries are raised per second. Every query read 100 MBs of data and consumed tens of billions of CPU cycles based on these queries. So the requirement was that they wanted to have a large, distributed, highly fault tolerant file system. Large to store, to capture, process huge amount of data. Distributed because they could not rely just on one server. Even if that had multiple disks stacked up, that was not an efficient choice. What would happen if this particular machine failed? What would happen if the whole server was down? So they needed a distributed storage and a distributed computing environment. They needed something which can be highly fault tolerant, right? So this was the requirement which Google had, and the solution which came out as a result was GFS, Google File System. Now let's look at how GFS works. So normally in any particular Linux system or Linux server, you would have a file system. You would have set of processes, you would have set of files and directories which could store the data. GFS was different. So to facilitate GFS, which could store huge amount of data, there was an architecture which had one master and multiple chunk servers, or you can say slave servers or slave machines. Master machine was to contain metadata, was to contain data about data. When we say metadata, we are talking about information about data. And then you have the chunk servers or the slave machines which could be storing data in a distributed fashion. Now any client or an API or an application which would want to read the data would first contact the master server. It would contact the machine where the master process was running, and client would place a request of reading the data or showing an interest of reading the data. Internally what it is doing is it is requesting for metadata. Your API or an application would want to know from where it can read the data. Master server, which has metadata, whether that is in RAM or disk, we can discuss that later. But then master server would have the metadata, and it would know which are the chunk servers or the slave machines where the data was stored in a distributed fashion. Master would respond back with the metadata information to the client, and then client could use that information to read or write into these slave machines where actually the data was stored. Now this is what the process or set of processes work together to make GFS. So when you say a chunk server, we would basically have the files getting divided into fixed size chunks. Now how would they get divided? So there would be some kind of chunk size or a block size which would determine that. If the file is bigger than the pre-decided chunk size, then it would be split into smaller chunks and be distributed across the chunk servers or the slave machines. If the file was smaller, then it would still use one chunk or a block to get stored on the underlying slave machines. So these chunk servers or slave machines are the ones which actually store the data on local disks as your Linux files. Client, which is interacting with master for metadata and then interacting with chunk servers for read-write operations, would be the one which would be externally connecting to the cluster. So this is how it would look. So you have a master which would obviously be receiving some kind of heartbeats from the chunk servers to know their status and receive information in the form of packets which would let the master know which machines were available for storage, which machines already had data, and master would build up the metadata within itself. The files would be broken down into chunks. For example, we can look at file 1. It is broken down into chunk 1 and chunk 2, and file 2 has one chunk which is one portion of it, and then you have file 2 residing on some other chunk server, which also lets us know that there is some kind of auto replication for this file system, right? And the data which is getting stored in the chunk could have a data of 64 MB. Now that chunk size could be changed based on the data size, but Google File System had the basic size of the chunk as 64 MB. Each chunk would be replicated on multiple servers. The default replication was 3, and that could again be increased or decreased as per requirement. This would also mean that if a particular slave machine or a chunk server would die or would get killed or would crash, there would never be any data loss, because a replica of data residing on the failed machine would still be available on some other slave server, chunk server, or slave machine. Now this helped Google to store and process huge volumes of data in a distributed manner and thus have a fault tolerant, distributed, scalable storage which could allow them to store a huge amount of data. Now that was just one example which actually led to the solution which today we call as Hadoop. Now when we talk about big data, here I would like to ask you some questions that if we were talking about the RDBMS case, take an example of something like NASA, which was working on a project called SETI, Search of Extraterrestrial Intelligence. Now this was a project where they were looking for a solution to take care of their problem. The problem was that they would roughly send some waves in space, capture those waves back, and then analyze this data to find if there was any extraterrestrial object in space. Now they had two options for it. They could either have a huge server built which could take care of storing the data and processing it, or they could go for volunteer computing. Now volunteer computing basically means that you could have a lot of people volunteering and being part of this project, and what they would in turn do is they would be donating their RAM and storage from their machines when they are not using it. How would that happen? Basically download some kind of patch on their machine which would run as a screensaver, and if the user is not using his machine, some portion of data could be transferred to these machines for intermittent storage and processing using RAM. Now this sounds very interesting and this sounds very easy. However, it would have its own challenges, right? Think about security, think about integrity, but those problems are not bigger as much as is the requirement of bandwidth. And this is the same thing which happens in RDBMS. If you would have to move data from archived solution to the processing layer, that would consume huge amount of bandwidth. Big data brings its own challenges. Huge amount of data is getting generated every day. Now the biggest challenge is storing this huge volume of data, and especially when this data is getting generated with a lot of variety, when it can have different kind of formats, where it could be viral, it could be having a lot of value, and nobody has looked into the veracity of data. But the primary problem would be handling this huge volume of data. variety of the data would bring in challenges of storing it in legacy systems if processing of the data was required. Now, here again, I would suggest you need to think what is the difference between reading a data and processing a data. So reading might just mean bringing in the data from disk and doing some IO operations, and processing would mean reading the data, probably doing some transformations on it, extracting some useful information from it, and then storing it in the same format or probably in a different format. So processing this massive volume of data is the second challenge. Organizations don't just store their big data. They would eventually want to use it, to process it, to gather some insights. Now, processing and extracting insights from big data would take huge amount of time unless and until there was an efficient solution to handle and process this big data. Securing the data, that's again a concern for organizations, right? Encryption of big data is difficult to perform. If you would think about different compression mechanisms, then that would also mean decompressing of data, which would also mean that you could take a hit on the CPU cycles or on disk usage. Providing user authentication for every team member, now that could also be dangerous. So that led to Hadoop as a solution. So big data brings its own challenges. Big data brings its own benefits. And here we have a solution which is Hadoop. Now what is Hadoop? It's an open source framework for storing data and running applications on clusters of commodity hardware. Hadoop is an open source framework. And before we discuss on two main components of Hadoop, it would be good to look into the link which I was suggesting earlier, that is companies using Hadoop. And any person who would be interested in learning big data should start somewhere here, where you could list down different companies, what kind of setup they have, why are they having Hadoop, what kind of processing they are doing, and how are they using these so-called Hadoop clusters to process and in fact store, capture, and process huge amount of data. Another link which I would suggest is looking at different distributions of Hadoop. Any person who is interested in learning in big data should know about different distributions of Hadoop. Now in Linux, we have different distributions like Ubuntu, CentOS, Red Hat, SUSE, Debian. In the same way, you have different distributions of Hadoop, which we can look on the wiki page. And this is the link which talks about products that include Apache Hadoop or derivative works and commercial support, which basically means that Apache Hadoop, the sole products that can be called a release of Apache Hadoop come from apache.org. That's an open source community. And then you have various vendor specific distributions like Amazon Web Services, you have Cloudera, you have Hortonworks, you have IBM's Big Insight, you have MapR. All these are different distributions of Hadoop. So basically all of these vendor specific distributions are depending or using on core Apache Hadoop. In brief, we can say that these are the vendors which take up the Apache Hadoop, package it within a cluster management solution so that users who intend to use Apache Hadoop would not have difficulties of setting up a cluster, setting up a framework. They could just use a vendor specific distribution with its cluster installation solutions, cluster management solution, and easily plan, deploy, install, and manage a cluster. So look into this link which talks about different distributions of Hadoop. Coming back, what is Hadoop? Hadoop is a open source framework for storing huge amount of data and processing it. It also depends on commodity machines and it does not need carrier class hardware. Now, when we say commodity machines, we are still talking about machines which are higher than a basic laptop or a basic server, but then they are not at the level of a carrier class hardware and costing huge to the organization. Hadoop as a framework has two main components, or I would say two processing layers. It has a storage layer which is called HDFS, Hadoop Distributed File System, and it has a processing layer which is called Yarn, which can handle different processing frameworks, in which Hadoop MapReduce is the oldest, most mature, and most evolved processing framework. HDFS derives its existence from GFS. It solves the issue of storing huge amount of data in a distributed fashion, and MapReduce is a programming model which allows to process data which is distributed across a cluster. We will learn on HDFS and MapReduce in further slides. HDFS is a storage layer. Now compare your laptop, compare your desktop. That also has a processing layer and a storage layer. Your disks are your storage layer. Your RAM and CPU core is your processing layer. Similarly, Hadoop as a solution has a storage layer, that is a distributed file system which can store huge amount of data in multiple machines instead of a single machine or a single server, which basically makes it highly reliable, highly fault tolerant, and distributed for parallel processing. Consider a data file of size 1 gigabyte. Now, if that was getting stored in one single machine, we would still have the data getting stored in one or multiple disks. And if you would try to read the data, the seek time taken to read the data would be very high in comparison to reading it from multiple machines. Now, HDFS, like your GFS, divides the file into smaller chunks and stores the data across the Hadoop cluster. In previous versions of Hadoop, the default block size was 64 MB. However, from Hadoop version 2 onwards, the block size is 128 MB. Now that's customizable depending on the average size of the data which is coming into the cluster. The block size can be changed. The minimum block size is 128 MB, which basically means that every file which is less than or equal to 128 MB would use one block, and any file which goes beyond the size of block will use multiple blocks, and these blocks would be residing on the underlying slave machines. Files are automatically split by Hadoop framework into blocks of default block size and stored across the cluster. Each node in your Hadoop cluster would have a bunch of disks that would be storing these blocks. Now, once we have the data stored in a distributed fashion, that also gives us the flexibility of going for distributed computing. And when we say distributed computing, we are talking about performing distributed parallel processing on large volumes of data. Take an example where we are talking about one single machine or one huge server which has 4 IO channels, and each input output channel can take care of 100 megabytes of per second, 100 megabytes of data per second. So if we have a data file of 1 terabyte, it would take approximately 43 minutes for one machine to process 1 terabyte of data. If you compare that with distributed computing, where we are talking about hundreds of machines, each machine having similar number of input output channels, and each channel having the same capacity to handle 100 megabyte of data per second, if a data file of 1 terabyte had to be processed in a parallel processing fashion using distributed computing, it would take just 26 seconds for 100 machines to process 1 terabyte of data in this environment. Now, all of you might be thinking that, yeah, this is right, but then what about the processing logic? That might be complicated. And yes, that would be, but then we have a MapReduce programming model and a processing framework to help us doing that. Now, when we look at one of the distributions of Hadoop, that is Hortonworks, it also has different resources that provide security to your big data. Now, before we start talking on these different services like Apache Knox, Apache Ranger, which basically allow you to monitor, authorize, and audit your Hadoop clusters, let's also look at the history of Hadoop, which started in 1999 with Apache Software Foundation. In 2002, where Nutch created by Doug Cutting and Mike Cafrella. Then Doug Cutting joined Hadoop and took Nutch product with him. 2008, Nutch was divided and Hadoop was born, and 2008 Yahoo released Hadoop as an open source project to ASF. In 2008, also Hadoop-based startup Cloudera Incorporated. Cutting left Yahoo for Cloudera. Yahoo was then coming out with Hortonworks as a commercial Hadoop distribution. MapR Technology also released Hadoop distribution. Greenplum released Hadoop distribution, and Pivotal HD. So this is a brief on history of Hadoop. You can always read about history of evolution of Hadoop, how it started, and today there are more than 10 distributions which are existing in market. However, Cloudera is the dominant one, and as per recent news items, Cloudera and Hortonworks have merged as one entity, which will bring up better solutions to the market. Now here we will want to learn on Hadoop ecosystem. So far we have learned on big data. So what is big data? We have learned on what are the different use cases where big data can be used, different organizations which use big data, and we took an example of Facebook. We also looked at Google file system, which laid the foundation for HDFS, the Hadoop's distributed file system. And we have not yet spoken about the processing layer, which is Yarn, and the processing framework, which is MapReduce, which we will discuss in future slides or further slides. Let's spend some time in understanding the Hadoop ecosystem, or you might have heard as ecosphere, which has various products, or you can say tools, or you can say packages which work together to comprise your Hadoop cluster. Now this picture shows the different components which are used for different requirements to work on your big data. Starting from bottom to top, we would look at HDFS, which is Hadoop distributed file system. Basically a file system which would use multiple machines to store the data. You have a processing layer, that is Yarn. We have a programming model, that is MapReduce, which could be written in any programming language, primarily in Java, but then that could be also written in Python or Scala or any other programming language. So these are the main components. So you have HDFS and you have Yarn. These are the processing layers, and for each processing layer we would have multiple processes which would be running on different machines within a cluster. Now what would a Hadoop cluster do if we did not have any data? And where would that data come from? So there might be a lot of sources where the data is getting generated, and that data might already be stored in RDBMS. And if you are interested in bringing in the structured data from your RDBMS layer to your Hadoop ecosystem, then you would use data ingestion tools like Scoop. So Scoop would be used for data ingestion, transformation, and pushing it into HDFS. Now that could also be used for exporting the data from HDFS back to RDBMS. But Scoop mainly is for structured data. Now you have other data ingestion tools like Flume, which is used for ingestion of streaming or unstructured kind of data. Data could directly be ingested into HDFS, or it could be going into a data warehousing package called Hive. Now Hive is a data warehousing package on top of HDFS where users could write their SQL queries to process the data. They could be creating their tables and databases to store the data, and that data would eventually be getting stored in HDFS and then in the underlying systems. Hive could be accessed through various services, and HCatalog is one of them. Your data which is being ingested could also be stored in a unstructured data store such as Apache HBase. Now there are lots of NoSQL databases. There are a lot of data ingestion tools. So if we go to Google and if we search for data ingestion tools, if I say data ingestion tools, so you could look at this link which shows around 18 different data ingestion tools which are existing in market. You have these tools for import and export, for transforming, for governance, for even processing the data while the data is being ingested. So you have Apache Kafka, which is a publish subscribing messaging system. You have Apache NiFi, which is not only for streaming or structured data, but it also helps with governance. You have Wavefront, you have Data Torrent, Amazon's Kinesis, Apache Storm, Samza, SyncSort, Goblin, Flume, Scoop, Samza, FluentD, Morphlins, White Elephant, Chukwa, Heka, Scribe, Databus, and many more. These are some data ingestion tools which can be used. Now we could also look at NoSQL databases, and if you just type in NoSQL databases, that can take you to nosqldb.org, and that would show you that there are more than 225 NoSQL databases existing in market. NoSQL stands for not only SQL. So these are databases which can be created without defining any schema. They could be key value stores, they could be document based databases which allow a lot of dynamism, which have different kind of constraints and can allow you to store your structured, unstructured or semi-structured data. So have a look at this exhaustive list of NoSQL databases. So coming back to your Hadoop ecosystem, your data could be ingested using one of the data ingestion tools into HDFS or into a Hive table or into Hive that would be using HDFS as the underlying layer. Your data could also be imported into a NoSQL databases such as HBase, which is a 4-dimensional database. It's a key value store which allows for faster random access across billions of records. We learn on HBase, on Hive in other sessions. Now, when you talk about Hadoop ecosystem, you could have a workflow manager such as Uzi. Now, there are other workflow managers like Azkaban, you have Luigi, right, which can be used, but Uzi comes with Hadoop. Now, not with Apache Hadoop. As I said, Apache Hadoop is an open source, and to set up a Apache Hadoop cluster and to set up Hive or HBase or any of these components, we would have to manually download the packages, edit the configs, set up the processes, and start the cluster and services. However, if you were using a vendor specific distribution, many of these packages would come as a packaged solution. So Uzi is a workflow scheduler which allows you to create a workflow of different jobs which could be run on a Hadoop cluster. You could have a service such as Zookeeper, which is mainly for management and monitoring. So it's a centralized coordination service, which especially plays a very important role when it is managing a high availability cluster of Hadoop or HBase. You have pig scripting, which allows for processing of data in a very concise way. You have Hive querying, which allows users to write their SQL queries to process the data. You could also do interactive analysis using packages like Apache Drill. You have Apache Mahout for machine learning. You have Kafka, Apache Storm, and even Spark, which can be used for streaming. Now Spark again has different components, and it is an in-memory computing framework which allows you to work on streaming data, structured data, graph-based data, and even machine learning algorithms. So Hadoop as such is a solution which allows organizations to work on big data, and Hadoop ecosystem and the components which are involved, which can be part of your Hadoop ecosystem, are growing. So there can be lots and lots of other components which can be part of your Hadoop ecosystem, which can be overall used to store, process, capture, and analyze big data. This is where we come to a point where we should now start learning on Hadoop distributed file system, which allows you to store data in a distributed fashion. HDFS basically makes it easier for organizations to store huge amount of data. In previous session, we were learning on big data, its characteristics, what are organizations interested in when they talk about big data, and different use cases. Today, we will learn on Hadoop distributed file system, which is basically the logical storage layer for a Hadoop cluster. HDFS is fault tolerant, is reliable, and is scalable. So let's understand and learn on the working of HDFS, that is the logical storage layer for a Hadoop cluster. HDFS is a distributed file system which is designed to store large volumes of data on commodity machines. It is designed with a low cost hardware, and that is what I mean when I say commodity machines. So we could have a cluster of tens and hundreds and thousands of nodes which can still scale and accommodate huge volume of data. It provides access to data across multiple Hadoop clusters. It has a high fault tolerance and throughput, and HDFS stores data in multiple servers instead of a central server. Now earlier when we were discussing on how storing data on a single machine can lead to more read or processing times and basically lead to high seek time, that can be taken care by a distributed file system such as HDFS, which would rely on file systems of multiple machines which form your Hadoop cluster. Now let's understand how HDFS works. For example, we have a large file which is to be stored on HDFS. Now that file would be broken down into blocks, and the block size by default is 128 MB. These blocks would then be stored across different slave machines or different nodes which are responsible for storing data. HDFS has a default block size of 128 MB, which can be increased as per requirement. Now that could be in megabytes, gigabytes, terabytes, or even bigger than that. The default block size is 128 MB from Hadoop version 2 onwards, and your previous versions of Hadoop had the block size of 64 MB. Here, the point to be remembered is block is a logical entity which basically takes the data and stores it on the underlying machines in their disks. Now this is how it would look. In a normal Hadoop cluster, we would have one single master, unless it is a high availability cluster where we could have multiple masters, that is two masters, one being active and one being standby. In a normal Hadoop cluster, you would have one master and multiple slave nodes where these data blocks are getting stored. Now, before we understand the MapReduce algorithm, let's also understand the working of HDFS and how data gets stored. Overall, how does it work? So let me just open up a notepad file and I would explain about HDFS. Now let's imagine that this is, I would like to have say 5 machines which could be forming my cluster. So I would have machine 1, machine 2, machine 3, machine 4 and machine 5. Now if I say my Hadoop cluster is running on these machines, which could be of a Apache Hadoop core distribution or having a vendor specific distribution such as Cloudera or Hortonworks or MapR or IBM Big Insight, etc. So these are some vendor specific distributions of a Hadoop cluster. Now here we can discuss later on how or what processes would be running on these machines. Now in case of Apache Hadoop cluster, to have a Hadoop cluster running, we would have to download the Hadoop related packages. We would have to untar, then we would have to edit config files to specify which processes would run on which nodes, and then basically we would be formatting HDFS, and then onwards we can go ahead and start our cluster. So it looks like in Apache Hadoop cluster we would have to manually do various things such as downloading the Hadoop related tar file, untarring it, editing the config files, formatting HDFS, and then going ahead and starting your cluster. In case of a vendor specific distribution such as Cloudera or Hortonworks, let me split it here. So you would have basically a cluster management solution that would help you in doing various things to set up your cluster. In case of a Cloudera distribution of Hadoop, you would have a Cloudera installer file, and then you would have a Cloudera manager which will help in deploying a Cloudera cluster. So downloading Hadoop related parcels or packages, untarring them, editing config files, formatting HDFS, and basically starting your cluster would be taken care automatically by Cloudera manager. In case of Hortonworks data platform, it would be Ambari software that would be used for deploying your cluster. Now, no matter which distribution of Hadoop you would be running, you would still have the same roles or processes which would be running. Let me just briefly discuss here about the terminologies. So let me bring up a file here which could explain these details. So let's look at this. Now here I have documented how it would look in different distributions of Hadoop. So we have Hadoop version 1 and 2, and let me just look for files. Yeah, so this is the one. Now if you would look in version 1 Apache Hadoop, we would call daemons or processes, and if you look at the names, we have the name node, we have data nodes, we have job tracker, we have secondary name node, and we have task trackers. In case of version 2, you would still call them daemons. You could have one or multiple name nodes. If it was a federation or a high availability kind of setup, you would have data nodes, Instead of job tracker, you would have resource manager, and then there is a temporary daemon called MR app master. If you had a high availability, then secondary name node would not be allowed, and if there was a federation kind of setup, secondary name node would still be existing. Instead of task trackers, you would have node managers. Now in case of vendor specific distributions such as Cloudera, whether you are talking about older version or newer version which is 5 point something, you would have what we call as roles. So in Apache Hadoop, we call them daemons. In Cloudera, we call them roles. In Hortonworks, we call them components, but we are talking about the same thing. In case of Cloudera, you would have services which would be part of the cluster, such as Impala, Uzi, Spark, Hive, HBase, Storm, Hue, HDFS, MapReduce, Yarn, and so on. Similarly, in Hortonworks also, you would have these services which would be running. In case of Apache Hadoop, we would not have so-called services seen, but then the functionality still exists. And how is that? That is depending on these daemons. So basically, if you look in Apache Hadoop or Cloudera or Hortonworks, everywhere we have these daemons, and we have these would be running on one or multiple nodes. So we could have different kind of setups, and just to briefly discuss on that, so we could have a name node running here, a resource manager running here, and you could have a secondary name node. Now don't go by name, it's not a second name node, we'll discuss about that later. A secondary name node, and then we could have data nodes running in machines. So this is one kind of setup where I'm talking about data node manager, and here we have a data node manager, and similarly we would have that on one more machine. Now this is one kind of setup. This is not the only setup possible. You could have a different setup where on the same machines you could decide to have data node and node manager running on every node. However, that would not be preferred because you wouldn't want the slaves and the masters to run on the same machine. However, this setup is also possible. You could have a high availability kind of setup, which basically is good for cluster and for an organization, where you could have name node 1 which would be running here, and say we can have a name node 2 running here. We could have a resource manager 2 running here, and then we could have a resource manager 1 running here, and I could still have my data node and node manager running in the same fashion. Now this would not be allowed in a high availability cluster because we have a standby name node. So this is one more setup which is possible, and then you could have a single node setup which could be everything having on the same machine, that is name node, resource manager, secondary name node, data node, and node manager. So these are different setups, and if somebody asks which is a preferable setup, then I would still go for either this one which has multiple data nodes and node managers, not this one, or your high availability setup. Now a single node or a pseudo distributed cluster is basically good for testing or some development kind of activities, and these are your distributed clusters. Now if we closely see, we basically have the roles or components or daemons running on these machines to take care of mainly two functionalities or two services, that is your HDFS, which is your storage layer, and Yarn, which is your processing layer. So in a Hadoop cluster, we have a storage layer and we have a processing layer. For storage layer, that is HDFS, you basically have one single master and you have multiple slave processes running. So I could say for HDFS to work fine, I should have a name node running, multiple data nodes running, and then a secondary name node running. For Yarn as a service, that is my processing layer, I would need minimum one resource manager and multiple node managers running on one or multiple machines. So these are the two layers, one being the storage layer and one being the processing layer. And for your storage layer, you have these processes wherein your name node is the master and your data nodes and secondary name node can be considered as the slaves. You have your resource manager as the master for your processing layer, and node managers are the slaves. Now this is briefly about the setup which could be in a particular environment. Now say the Hadoop related packages or parcels have been downloaded, whether it is a vendor specific distribution or Apache Hadoop cluster. Say untarring of that is done, editing of config files is done, formatting is done, and your cluster is started. In that case, your cluster would be up and running, and then we could basically have, and once your cluster is up, we would have the HDFS up and running, ready to allow us to store data. Now let's imagine that this is my HDFS, which is up and running, or HDFS as a service is up and running. Let's imagine that these are my nodes, which is M1, M2, M3, M4, and M5. Now while the config files were edited for each of these nodes, it would have been defined which processes will run, and we would have also given path where these processes will store the data. So let's say that this is my M1, this is M2, M3, M4, and M5. M3, M4, and M5 have data nodes running. So we would have defined a path. Let's call it, say, ABC slash data, ABC slash again data, or D, and ABC. So this is the path which has been defined on every node to store Hadoop related data. And on M1, where we would have name node running, we would have still defined a path. Let's call it ABC slash N, where name node could store its data. So once your cluster is up and running and your HDFS is available, we can have our data stored on HDFS. Now let's understand how does that work. So any client or an application which would want to write data to the cluster needs to interact with the master to begin with. Let's say client, machine, or an API or an application would be interested in writing the data. Now how would NameNode know about available data nodes? So as soon as the cluster comes up, the first thing which happens is these data nodes would be sending in their heartbeat to the name node every 3 seconds. So data nodes send the heartbeat to name node every 3 seconds to let the name node know, to let the master know that they are available. What does name node do with this? Name node is building a metadata in its RAM. So it already has some metadata in the disk which was created as a result of formatting HDFS, and now we would have metadata in RAM which is getting built. So initially name node would have information of which data nodes are available in the cluster. Now if a client or an application wants to write data to the cluster, it gets in touch with the name node inquiring about the slave machines or inquiring about the data nodes where the data can actually be written. Your name node refers to the metadata collected so far and responds back mentioning the data nodes or the slave machines which are available for data storage. Based on this response, your client takes the file to HDFS intending to write it to the cluster. Now in Hadoop, we basically have two things. One is the default block size, which we discussed earlier, is 128 MB. So you have 128 MB as the default block size, which is customizable and that can be changed depending on the average data size. And you have the default replication, which is 3. Now imagine the application or API or client would want to write a file which is 256 MB, which is bigger than the block size, and this file has to be broken down into what we call as blocks, which are logical entities. So the file is taken to the framework. Framework will split the file into blocks. So let's imagine that this file is 256 MB. It will be broken down into two blocks, B1 and B2, and these blocks will then be randomly distributed to the slave machines, that is the data nodes. So we would have block 1, say, getting stored here. Now you could also have block 1 getting stored on any of these data nodes. So we would have block 1, and then we could have block 2 which could be written here, and then you would also have their replicas sitting on the machine. So the rule of replication is you will never have two identical blocks sitting on the same node. So if I have block 1 here, then I will never have a replica of block 1 again on the same machine. So we will have a replica of block 2 here, block 1 here, and you have a replica of block 2 here. There is no differentiation between which one is the original and which one is the replica. For the cluster, all the blocks are same. And what also happens is, after the blocks are written, your data nodes are repeatedly sending their block report to name node every 10 seconds. And this information is again updated in the name node's metadata. So now name node will have information what are the files. The files are broken down into what blocks. The blocks are residing on which data nodes. And this metadata is getting built in the name node as data nodes respond with their heartbeats and also every 10 seconds with their block report. Now we need to remember one point here, that name node is basically a master and data nodes are the slave. Hadoop as a framework has been coded in Java, which basically means that every directory, every file and file related block is considered as an object which is getting stored. And for every object which name node is tracking, 150 bytes of name node's RAM is utilized, which also tells us that if the block sizes were smaller than 128 MB, then for the same file we would have more number of blocks, which would mean that name node's RAM would be overutilized and overload name node. So block size has to be chosen with a lot of consideration on the master's RAM and what is the average size of the data. Now this is how the data is distributed in blocks and distributed across the data nodes. Thus HDFS is very fault tolerant, because if any of the data nodes fail, then you still have other data nodes which have the replica of data, thus making it possible to read the data and access the data even if multiple data nodes go down. Now there are other internals, that is how data nodes are placed in racks or what has rack awareness to do in block placement, but we will learn on all that later. So this is how your HDFS works. Now there are many other things such as the read and write process, which is taken care by your methods such as open and create, which internally are playing a role when a read or write operation happens. Also, facts like replication is a sequential process, but write activity is parallel. So we can learn more functionality of HDFS in later sessions, but this is in brief on how HDFS works, how your file is split into blocks, and the blocks are getting stored on the disks. Note that the block contains the data. So even if you have a file which is 1 kilobyte, and if this file is to be stored on HDFS, it will still use a block of 128 MB, which does not mean that there is a disk space getting wasted. When the block resides on the data node's disk, it will only occupy 1 kilobyte of space for the data it has, which means that block is a logical entity to take your data to the disk and get it stored on the disk. This is how your HDFS works and basically takes care of reliable data storage across machines in distributed fashion. Now that we have set up a 2-node cluster which has 2 data nodes, 2 node managers, 1 master machine, let's try working with HDFS. Let's look at quick commands which allow you to write data to the cluster, although there are different ways. The first way is using commands. The second is using an IDE, and where you could write your code to use Hadoop's file system API. And the third is a graphical user interface called Hue, which normally does not come with Apache, although it can work with Apache. It comes as a service with Cloudera and other distributions. To work with HDFS, we need some sample data. Now there are various websites from where you can get some sample data. So you can open up your browser and let me show you some sample places or sample data set links from where you can download bigger or smaller files, which then can be used to write data to your HDFS. Although you could just pick up a local file or you could create your own files and write them to HDFS. there are various dataset sites which can be used. So for example, you can type in machine learning UCI datasets, and this is one link which has more than 200 datasets which can be used for even data science kind of activities, which can be used for testing with your algorithms, and you can download data from here onto your local machine, and then from your local machine we will be writing the data to HDFS, which then based on the size of the data splits the data into blocks, and your blocks would get stored on your underlying machines wherever data nodes run. So I can click on this UCI machine learning repository, or even just on data sets to be very specific. All we need is some sample data sets. You can get Kaggle data sets, you can get data sets from Yelp website which are bigger data sets zipped, and you can be using them to write data to see how your file split into multiple blocks. Now here we have a lot of data. We can click on any one link to begin with, and here I have the data folder, shows me the some file, and I can just right click on this, save link as, and save the file. This is a simple text file and we can save it. And you can get various data sets from here. You can even go to Yelp dataset challenge, and that has bigger files which are zipped and they can be downloaded. So you can click on download dataset. Although I will not start the downloading here, you can just give in your name here, just some email ID, some initials, and you can click on download. So this is one more website where you can download the JSON datasets, which are 3.6 gigabytes in compressed format, and then you have photos which are in 7.2 gigabytes. You can also say Gutenberg download books, and that is again a website from where you can download free datasets which are not very huge. So try to get some variety of datasets in different formats which then you can write to HDFS. You can even use your HDFS log files which already exist on your machines, and you don't need to download anything from internet. Now let's close this for now. So I already have some file. Let's copy this from home, HTC downloads. That was my file. Let's copy it to home HTC, and here's my file. I can check the permissions. So that's owned by HTC. I can even look into user local Hadoop logs, and there are some already log files. So you can even copy some of these files using copy user local Hadoop logs, and let's take Hadoop data node related log, and let's copy it to home HDC for our testing. And now we have some other files. Now to work with HDFS, as I said, you can always type in HDFS, and that shows you various options. Now we already used the first option, which is name node hyphen format. We also used HDFS admin to look at how many nodes we have, and to work with your HDFS file system, the option is DFS. So you would say HDFS, DFS, and then you can always hit on enter, which shows you various options to work with your distributed file system, like creating a directory, copying some files, getting data from your HDFS to your local machine, changing the permissions, changing the replication, and many other options. So here, let's click on HDFS, DFS. Let's create a directory and let's call it my data. So this is a directory I'm creating on HDFS. Remember, this directory will not be seen on your local machine. It is a HDFS directory. Now if I look in my root, I don't see my data because that's a HDFS directory which is technically getting created on HDFS, and once you start writing data to HDFS, the relevant blocks will start getting stored under ABC/data. So as of now, we can always keep a browser open to see, as we work with HDFS, how does the data propagate or come to your distributed file system using the web interface. So here, let's say http://m1.5.0.0.70, and that's my browser interface. Let's click on utilities and let's click on browse the file system, which should show the directory which we have created, although that does not have any data as of now. Let's go in here Now we know that we have some files here. So I will say HDFS, DFS, and this has two options. Either I can say put or I can say copy from local. Both of these do the same thing, and both of these you can find here. So we have put and we should have copy from local. That is, you're copying the data from your local machine to your HDFS. So now I will say copy from local. I will say take the ABA directory or file and put it in my data. So now I'm technically copying a file from my local file system to my HDFS, which is then using again my local file system's path. So this is done. Let's quickly check by clicking on my data if my file is written. Now if you see, this file is 187 kilobytes. However, this will still use a block of 128, and in my previous sessions I already explained why a block of 128, but when it goes to the disk it will only occupy the space for the data the block has. We can quickly go in here and we can do a HDFS DFS listing of my directory, which should have my file now, and we can quickly check if my file is replicated either using the web interface which says replication is 2. That means the file related blocks should be getting stored on the underlying data nodes. We can always click on overview if we would want to browse and scroll down, which says there are 3 files and a directory. The file has 1 block, so totally you have 4 file system objects. We can scroll down to show or see we have 2 live nodes, and if you see, each node has 1 block. We can always look from our data path by looking into abc/data/current that has block pool directory, that has current, that has finalized, that has subdirectory, and the block. Look at the size of the block. It is 191, which relates to the kilobyte size which we are talking about. Similarly, we can check on M2 machine, which also has a data node running, to make sure our file related block is replicated. So look in block pool, current, finalized, subdirectory, and that shows me the same block which is replicated with its meta file and with the same size. This ensures that my data is getting replicated as per whatever factor we have set, and my file is written to HDFS. And now I can also do a complete listing. I can just say a recursive listing to show me all the directories and all the files which I have in my HDFS. I think we are forgetting something. We are logged in as root, which is not right. So we need to be logged in as HTC, and then we can try our commands, that is HDFS DFS-ls/ which should show me my directory. But then if you would want to do a recursive listing of showing all the directories and files, you can just add -r. So we have written a file to HDFS in my data directory. Similarly, I can write using a put command. Last time we used a copy from local. I will use a put command. I will say let's take this log file and let us write it to the my data directory. Instead of copy from local, I am using a put command, which also allows me to write the file to my HDFS. Once this is done, let's go to the web UI and let's go to browse the file system. Let's look in our directory, and that shows me that I have a log file which is even smaller than the first file which we wrote. It is in kilobytes. However, it is replicated. It is using still the block size, and we can always go back and look at the terminal to see if for my new file I have a new block which should be in my data path. And if you see this is my block, which will also have a replication on machine 2. So this is how you write one file, or you could write multiple files. Let's create some files here. So I have these log files. Let's say Hadoop log, and let's give it a name like this. So now if you see, I just created multiple files, and I can also say HDFS DFS make directory, let's say my data 2. So I'm creating a new directory on my HDFS, and then I can even copy multiple files or a complete directory. So all I need to do here is give a matching pattern or a directory. So I'll say HDFS DFS put and then I can say take all the directories files and put it to my data 2. Remember, this one file or multiple files are following the replication what has been set at a cluster level. Now if we do a recursive listing where I would want to see all the directories and the files which are within my HDFS, I see that I have a my data directory and I also have a my data 2 directory which has multiple files, and all of the files within the directory are following the replication set at a cluster level. So all of them are having their blocks replicated twice. We can always go back here. We can just do a back, and that shows me what I have in my data 2. Everything is replicated twice. What I have in my data is also replicated twice. Now HDFS also has a functionality where you can write data with a different replication. So let's create one more directory, and now let's write data with a different replication. So the way I write my files, I follow the same thing. However, now I will say -dfs.replication and I will specify it as 1. So I'm passing in as argument and I'm specifying that I would want to write data with a replication of just 1. So my blocks will not be considered under replicated, and I'm choosing to write these files in this directory with a replication of 1. We can check from our browser interface by just doing a quick refresh. And here if I click on my data 3, it shows it follows a replication of 1. There is also a command to check your replication status using HDFS. So we can say HDFS fsck/files/blocks, and if I would want to see only blocks or only files, I could choose one of them. Now here I have given a complete HDFS file system. I can replace that with /my_data. So I can say my data 3. This is what I would want to see, and this will show me within this directory how many files I have, how many blocks does each file use, and is it replicated correctly. So my fsck command gives me an information that in my data 3 I have one file which is 24 kilobytes, uses one block because it is very smaller than 128, and it is replicated only once. So there is no situation of over under misreplicated blocks. We have our files correctly replicated as they were specified while writing. Same thing can be seen for other files, say my data 2, and that will tell me that all the files within my data 2 were replicated as per the default replication which was at a cluster level. And if you see here, everything is replicated twice. We don't have any over under misreplicated blocks, and my file system status is healthy. So this is the HDFS command to make sure that your files are replicated correctly. So we have seen how your files are written with default replication. We have seen how your files follow a dynamic replication what you specify on the command line. Now we can also see a command which allows us to change replication after the data has been written. So I can say set rep and I can say path, that is my data 3, where I initially had all my file related blocks replicated only once, and now I'll say my data 3 and I can specify that this should follow a replication of 2, which basically means that it will look into the directory, it will check all the files which had only one block, and now it will create a replica of those blocks across other data nodes. We can always go back and look into the data node logs to see the replication happening. We can also look from the browser interface, which initially was showing a replication of 1 and now it shows a replication of 2. So this is the command to change the replication after the data has been written. So our writes can have default replication. We can write files with a different replication. We can change the replication after the data is written. Not only that, we can even get the data from our HDFS to my local machine, and for that I'll give HDFS get command or copy to local. So I can say my data 3 and then I can bring it to my local machine in home HDC using a get command. So this is to get data from your HDFS to your local machine using a HDFS command. Now if you see, I should have a my data3 directory which is in my local path, and we can look in my data3. It has all the files which we had on HDFS. So we were not only putting data from our local machine to HDFS, we also successfully brought data from our HDFS to local machine. We have written data with different replication. We have checked the status of nodes. We have checked the status of blocks, and if we would want to delete some data, HDFS also has options for that. So I can say HDFS DFS remove, and I could also do a recursive remove to remove everything including the directory from my data3. So this will delete data from my HDFS. However, if thrash is enabled, now thrash basically means recycle bin, which depends on a property in the core-site file. We have not enabled it. If thrash is enabled, then your data will be deleted from HDFS. However, it will not be permanently deleted. It will sit in thrash for a time interval what admin has specified in the configuration file. So right now I deleted thrash, and this seems to be gone from HDFS because we have not set up any thrash. However, if a thrash is set up, then either you can decide to have your data deleted and still be in thrash so that it could be restored, or you could delete it permanently using a skip thrash option. However, remember, this skip thrash option makes more sense if the thrash is enabled in your cluster and you do not want your deleted data to be sitting in thrash even for whatever time interval has been set. Because even if the data sits in thrash and your thrash is a directory structure on HDFS, all the data will still be replicated. So we have seen how you can write data to the cluster, how you can get data from cluster to your local machine, how you can write it with different replications, how you can delete it from your cluster, and do a recursive listing of your directories and files. Now there are various other commands which can be used. For example, something like copy or move or change permissions and many more. So the more you would want to try, type in HDFS DFS, and that shows you different options which can be used to practice working with HDFS using commands. We will spend some time in learning on one of the oldest and the most mature processing framework, that is your MapReduce. Now there are a lot of processing frameworks, and basically Yarn, which is the processing layer, can handle different processing frameworks in a Hadoop cluster. We will learn about Yarn in further session, and here let's spend some time in understanding the MapReduce programming model, or as you call it as MapReduce algorithm, which is one of the oldest and most mature processing frameworks. Now there are various processing frameworks which you can search for. Now let me just show you a useful link. You can just go to Google and type in MapReduce, or you can just say computation frameworks O'Reilly, and that should show you the processing frameworks for Hadoop. Now this is one of the good articles which explains about processing frameworks for Hadoop. Now, if you read through this, which tells Hadoop has become the de facto platform for storing and processing large amount of data and has found widespread applications. And in Hadoop ecosystem, you can store your data in one or one of the storage managers such as HDFS, HBase, or even Solar. And then you can use processing framework to process the stored data. Now here we have listed down various processing frameworks. So you have Apache projects such as Hive, Pig, Spark, Cascading, Crunch, Thais, Drill, along with Impala and Presto. Now one of the key things which anyone would think about is when you look at so many processing framework options, which processing frameworks are most commonly used, or how do I choose which framework to use for my specific use case. Now in this article, if you read further, it talks about categories of processing frameworks, like you have general purpose processing framework, you have abstraction frameworks, you have SQL frameworks, you have graph processing frameworks, machine learning frameworks, and real-time streaming frameworks. So these are high-level categories, and here it also shows you basically which of these frameworks are dependent on HDFS, or which of these frameworks depend on MapReduce. So here is a list of processing frameworks like Hive, big cascading, crunch, graph, mahout, which depend on MapReduce. Then there are some which depend on Spark, which depend on Taze, and then you have the independent ones. And these can be categorized as general purpose execution engines or processing engines. You have SQL engines, you have abstraction engines, real-time frameworks, graph processing engines, and machine learning engines. If you read further in this article, it details about different processing frameworks, what are the major criterias in which an organization might decide on using a processing framework, which mainly depends on the use case, and it also depends on the expertise which an organization has. So I really suggest a read through this link which talks about different processing frameworks. Now, in general, we can understand one thing, that if your organization is intending to process huge amount of data, if your organization is interested in processing data for different use cases, then it has to select the appropriate processing framework. Now, as I said, it depends on the expertise, it depends on the use case, and then it depends on organization's appetite for the cost which it is ready to incur in choosing one processing framework. Now, coming back to our topic, that is MapReduce algorithm or MapReduce programming model. Now, as I said, it is one of the oldest and the most mature processing framework, which means that it came into existence with Hadoop as a framework, and then it evolved over years. Right, so there are a lot of bug fixes, there are a lot of patches which have taken care of issues which were initially noticed when users started using MapReduce programming model. Now, Google introduced MapReduce programming model in 2004. Now, we have already discussed about GFS, the Google file system. Now, we can think about this as a processing framework which helps you in processing the data in a distributed fashion. Now, before 2004, data was stored most probably on a single server. Now, that can mean that it was getting stored in the underlying file system, or it was getting stored in the databases, where the seek time, the time taken to read the data, the time taken to process the data was obviously very huge. You had very less fault tolerance in cases if the single machine or the single server would fail, and obviously it was more time consuming and more complex. Now, after 2004, data could be stored and processed on multiple servers. And this also gives a possibility of analyzing or processing the data in real time. So it was not only bound to batch processing, but then you could also do real time processing. Now, what is MapReduce? As the word says, MapReduce basically has two main phases. You have the mapping phase and you have the reducing phase. Now, at high level, you can understand that mapping phase is something which sorts the data. Although it just does not do the sorting, mapping basically means applying a kind of function or applying a kind of computation on every element. And it does involve some kind of sorting and shuffling. It does involve some kind of decision making in how much amount of data is being processed. Now, we already know from our learnings of HDFS that our data, when stored on HDFS, is divided into blocks, and those chunks get stored randomly on the underlying data nodes or underlying slave machines. So MapReduce is a programming model. Now, it need not be, or it necessarily is not written only in Java. It can be written in Python. It can be written in any other programming language. However, it follows a strict paradigm, that is mapping and reducing. So mapping is one of the phase, and reducing is a phase which aggregates. So reduce segregates data into logical clusters, removing bad data and retaining the necessary information, or you can say it does aggregation. Now, when we talk about MapReduce operation, let's just look at this. So you basically have input processing or inputting, you have splitting the data, then you have the mapping phase or basically a map function, then you have internal shuffling and sorting which happens, and finally it is the reducing phase which aggregates the data. So MapReduce algorithm is used for data processing. Now, it basically has these two phases, mapping and reducing, which are determined by the developer. So basically, it's the developer who will write the code for your mapper function and will write the code for your reducer function. It is used for data processing, and basically it does in two main phases, that is mapping and reducing. Now, going back here, let's have a little more understanding and explanation on how MapReduce works, although we will learn details in further coming sessions. Now let me just open up a notepad, and as I said, when you talk about MapReduce, you're talking about mapping phase. Now this is taken care by a mapper function which is provided by the developer or provided by an individual who is developing a solution which will use the MapReduce algorithm or MapReduce paradigm. And what does this mapper function do? It does map tasks. Now that could be one or many depending on the splits. You have the reducing phase, which is taken care by the reducer function, which basically is running the reduce tasks. Again, they can be one or many depending on what is the kind of data you are processing, what are the configuration settings, or basically depending on the kind of processing which is required. To break them down, so we can say, for example, let's assume a file which is say, let me call it as hadoop.txt, and this file has some content. Say this is a new learning, we are learning MapReduce. It is a programming model, processes data in two phases, map phase, reduce phase. Now let's imagine that this is a file which you would want to process, and let's take a standard example of word count which an individual wants to do on this file. Now if this file was stored on a Linux file system, then you have other utilities which could be used to do a word count. Now if we want to do a processing of this file, where I would want to find out how many times a particular word occurs in a particular file, and let's imagine that we have a cluster which is of two nodes, data node 1 and data node 2, and let's also imagine that this file, when it was stored on HDFS, gets split. Imagining or assuming that this file is bigger than 128 MB, this file is broken down into two chunks or two splits. One gets stored here and one gets stored on my second node. Or you could also imagine both the chunks getting stored on data node 1 and then having a replica on data node 2. Now once the file is split, what you would want to do is you would want to do the processing of this file to do a word count. And as I said, the first phase which will start doing the processing will be your mapping phase, wherein you would have a mapper function, and the code which would be written for this mapper function, what it would do is, to do a word count, we would want to basically first list down how many words we have, and then individually we would try to give a value to the word so that later we can add those values. So that's what my mapper function will do. And as I said, your mapper function triggers map task, or I can say map tasks. So that could be one or more depending on the splits. And by default, the split size is equal to the block size. Now that can again be customized. So here we can say that once my mapping phase starts, there would be two map tasks which would run on the data which is in data node 1 and on the data node 2 parallelly. So you have the mapping phase which will start breaking the records into individual elements. Let's say this is my word. So I will say every word is being taken out from the record and then it is being assigned a value 1. So this is what my mapper function is doing. You could have written the code in a different way. So mapper function or the map task is basically breaking the records into individual elements and giving you a list of data elements. And what are these data elements? These are your key value pairs. These are your key value pairs where your key is the word and the value is number 1. Similarly, this would be happening on data node 2. So we can again say there is a map task running on data node 2, and what it does is it works on the records, breaking them into individual words and assigning a value to them. So that would be your key value pair. Now once this data or once this processing is done by the mapping phase, this data is not my final result. It is an intermittent data. So to have aggregation of this data done, we basically need to have some kind of sorting and shuffling, which will bring the similar keys together. So that depends on sorting and shuffling, which is taken care by the processing framework itself, which will bring all the similar keys together. Now, there is also something called as partitioning phase, which basically decides on how many reducers would be required to aggregate this data. It depends on the type of keys. So here all my keys are words. So basically I could have reducer function and the logic written in reducer function, which can consider keys, which are words, and then aggregate their values if you have repeating keys. So partitioning phase decides on how many reducers would be involved. Now, how many reducers would be involved also depends on configuration properties which are set at a cluster level. Once the partitioning phase is done, then we could also have a combiner phase, which is basically a mini reducer, or it basically does the same reducing what your reduce function will do. This is optional. And finally, you have the reducing phase, which is taken care by the reducer function. Again, a reducer function is developed or provided by the developer, which takes care of reduce tasks. And what do your reduce tasks do? Your reduce tasks will work on the data coming in from multiple map tasks and basically aggregate them. So if I have a word which is repeating twice, then basically you will have its value which will get aggregated. So this is your MapReduce, which basically has mainly two phases, the mapping phase and the reducing phase. And in between you have sorting and shuffling, which is taken care by the framework itself. You can have the partitioning phase, which basically decides how many reducers would be used or how many reduce tasks would be used, or that could be dependent on the configuration settings. And then you have the combiner phase, which is optional, which is basically a mini reducer. So this is how your MapReduce works. And it basically takes care of processing your data in a parallel fashion across machines, and it obviously depends on the locality reference. Now, as I mentioned, that your data which is stored on HDFS gets stored on the underlying data nodes, and as we took an example of a file being split, so the map task will run on the machine where the relevant data is, which also means that the processing layer will take care of resource allocation on the nodes where the data resides. Now this is how your MapReduce helps in processing huge amount of data in a parallel fashion. I would also like to share one more good link which talks about MapReduce. So we can search for MapReduce tutorials from Yahoo, and here you can look at the diagram which explains the mapping and reducing and how basically it works on taking care of your processing. So let me just refresh this and let me check. So probably this image is not displaying now, but then you can check at a later point of time, which basically shows you a sample code for the mapper function, that is your mapper class, which will have the map task, and it has the reducer class which basically has the reduce task, and then it should also be showing you an image which shows in total how it works. We'll discuss about MapReduce in a later session where we'll discuss in detail about the different phases which are involved in MapReduce. So thank you and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.